Okay, so in this video we're looking at pages 8 and 9 of your notes, and we're just going through the final purification stages of the bromobutane experiment. Okay, so we've distilled off our impure product and we're putting it into a separating funnel. This is what a separating funnel looks like. So it's important that you can draw it correctly. You don't have to go in this much detail, but it's got a tap at the bottom, it's got a narrow opening at the top, and it's usually got these straight sides here. So do make sure you're able to draw that. Now when you put it into the separating funnel, you're going to see that there are two layers. There is an aqueous layer and there is an organic layer. Now to work out which layer is which, we need to look at the density data. Don't do what I did with my first year undergraduate labs and I misread the density data and threw away the wrong bit. So you've always got to be very careful with this bit. Now water has a density of 1 gram per centimetre cubed, and the stuff we want is bromobutane, which has a density of 1.3. So in this case, the 1 bromobutane, the organic layer, will be underneath the aqueous layer. So in this case, this is going to be my organic layer, and this is going to be my aqueous layer. So they're still going to have impurities in both of those layers, but we're going to have an aqueous layer sitting on top of my organic layer. The reason that they don't mix is that the organic is insoluble in the aqueous. So that's why they don't mix, they're immiscible. So then what I can do is I can just tap off this bottom bit, and I don't need to keep that top aqueous bit. As I said, I would usually just put it to the one side. Okay. So when I've done that, I can then add some concentrated hydrochloric acid. What the concentrated hydrochloric acid will do is it will pronate the butanol, and that will make it more soluble in the aqueous layer, because even though it's concentrated, it's still aqueous HCl. So when I give it another shake, you will see again you've got an aqueous layer and an organic layer, and again I can tap off the organic layer and I can tap off the aqueous layer and separate them out. So I've done my first separation, I've added my conc HCl, given it a bit of a shake, and I've tapped it off again. Now what I'm going to do is I'm going to add a solution of sodium hydrogen carbonate. Now this is going to react with any of the acidic impurities. Again, I'm going to get my two layers. I'm going to get an aqueous layer and I'm going to get my organic layer, which hopefully contains mostly now my bromobutane. So I've got rid of any acidic impurities. That could be any leftover HBr, any dissolved sulfuric acid, and any HCl that I've already added from step 1. Last but not least, I'm going to dry it. Now it might sound a little bit strange that we're drying a liquid, but all that drying means is I'm removing water. So I add anhydrous sodium sulfate. There are other drying agents I could use, but this is a good one. And what you will see there is that my mixture goes from a cloudy solution to a clear solution as the droplets of water are removed. The sodium sulfate stays as a solid because it's very insoluble in organic solvents, and you can just filter it off. Okay, so we're now just going through the questions at the bottom of this page. So we get these two layers in our separating funnel when we shake it with any aqueous reagents, and that is because the bromobutane is immiscible with water or in water due to its lack of hydrogen bonds. So it can't do hydrogen bonds with the water, so it's not energetically favourable for it to dissolve in water. So we say it's immiscible, it doesn't dissolve in water. So when I shake it with hydrochloric acid, the butanol will be pronated. So the HCl pronates, that means it adds a proton, it adds a hydrogen ion, pronates the butanol, which makes it more soluble in water. It's already quite soluble because it's got an OH group, but because it's got this long carbon chain, it will also be significantly soluble in the organic layer. So to make it more soluble in water, we can pronate it. We can add a hydrogen onto this. When I shake it, the solution with sodium hydrogen carbonate, that removes any acidic impurities. Okay, so that could be the HCl, the HBr, or the H2SO4. So it removes all of those. There's a marked buildup of pressure after shaking because CO2 is produced. The ionic equation for this is all the hydrogen ions from the acid react with the hydrogen carbonate, HCO3, and those are both aqueous because they're both water soluble, and that's why you get carbon dioxide gas and water as a liquid. So that's your basic hydrogen carbonate acid reaction. Now this next question, very important, why sodium hydrogen carbonate solutions is used rather than sodium hydroxide solution. Okay, so sodium hydroxide, or at least the OH negative part of it, is a strong nucleophile. That's what we generally use it for, a very good nucleophile. Now, if I was to add something containing sodium hydroxide to my halogenoalkane, that hydroxide ion would react with it very quickly to make the alcohol and to kick out the bromo. So I've just spent a double lesson, and probably most of the next double lesson as well, carefully making my bromobutane. If I got sodium hydroxide anywhere near it, it would pretty much instantaneously react back to form the alcohol. So you definitely do not want to use sodium hydroxide solution to neutralize the acid. Much better to use sodium hydrogen carbonate. We very rarely, if ever, in fact I can't think of a time when I would use OH negative to remove acid impurities, because it will pretty much always react as a nucleophile and mess everything up. So, on to the last couple of questions. How did your appearance of your product change when it swirled with the anhydrous sodium sulfate? Well, it went from cloudy to clear. So it went from a cloudy solution to a clear solution. Now, the reason for this is because we are removing water. What you've actually got here is an emulsion, but a rather unusual emulsion. Usually, emulsion is fat droplets suspended in a liquid, in an aqueous liquid. In this case, it's droplets of water which are suspended in an organic liquid. So by removing the water, you go from a cloudy to a clear. Now, there are other ones that you could use in place of anhydrous sodium sulfate. You could use anhydrous calcium chloride or anhydrous magnesium sulfates. Okay, but the one we generally choose is anhydrous sodium sulfate. Anhydrous simply means without water. Okay, so this is the last step in the purification of our bromobutane, and it's also a way of testing its purity. So I have here set up my simple distillation. I know that the boiling point of my 1-bromobutane is 102, so I'm going to collect anything in the range of 100 to 104. So in other words, 2 degrees either side of that boiling point. That'll take into care any errors of my equipment. Anything else that is not bromobutane should remain in the flask or distill off before this point. So just to remind you about simple distillation and a couple of key points. Water goes in at the bottom, comes out at the top, so that the inner tube here is always surrounded by water. We don't get any hot spots, and it allows the most efficient cooling. We're heating our sample here. We should also include anti-bumping granules here. This part of the apparatus is sealed, so no gases can escape. Remember, gases are like students. You need to cut off their escape routes. We want the gases to go up here, come down, condense on the cold wall of condensers and drop into our collecting vessels. If you have big gaps here, they'll just go shooting out the sides. The bulb of the thermometer, this thing here, has to be parallel with this side arm. That's so that we're measuring the temperature of the vapour that we're actually condensing. And lastly, this end of the apparatus needs to be unsealed. We need a space here so that we don't get a pressure build-up. Okay, so we're just looking at the last set of questions. So explain the term fraction to describe the sample. So it's parts of the sample having a narrow specified boiling points. So it's a narrow specified boiling point. How does this allow you to check the identity and purity of the product? Well, it should all distill over at 102 degrees Celsius. Any impurities will just lower this boiling point, so you wouldn't get a nice clean product at 102. Okay, so the next bit of this, we are going to need to make some numbers up because obviously we don't have our masses with us. So we're going to write out a balanced equation for the production of 1-bromobutane from butan 1-ol. So nice and straightforward, we've got our butan 1-ol, so CH3, CH2, CH2, CH2OH, and to that I'm going to add my hydrogen bromide, and that's going to make my water, and it's going to make my CH3, CH2, 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 Br as my product. So the mass of butan 1-ol that I used, well, mass is equal to density, mass is equal to density times volume. So the density is 0.81, we saw that on the previous page, and we're going to say we use 7.5 centimetres cubed, so that gives me a mass of 6.075. Okay, so then we're going to calculate the maximum mass of bromobutane that I could be produced from this amount of butan 1-ol. So we're going to get our moles of my butan 1-ol, moles of my alcohol. Well, moles is mass, 6.075, divided by the RMM, which is 74, and that gives me a moles of 0.08209 moles. We know from our equation that it's a 1-to-1 molar ratio. Therefore, we should, if all of this is converted into bromobutane, therefore we should get 0.08209 moles of bromobutane. So to find the mass of the bromobutane, I'm just going to times that moles by the MR, 0.8209 times the MR of 1 bromobutane, and that's 136.9. So we should get a maximum mass of 11.24 grams. That's my percentage, that's my theoretical yield. So that would be the highest amount I could possibly get starting with this mass of butan 1-ol. Now, making up a number, let's say my final mass was 6.8. 6.8 divided by my theoretical times by 100, and it gives me about 61%. Slightly unrealistic, but what the heck, this is just theoretical anyway. So experience suggests you would do very well to get this yield. This is highly unlikely. You're more likely to get a yield of less than 50%. So there are various reasons for this. Firstly, side reactions. As you can see from the number of impurities we had, there are lots of other products being produced. Secondly, we have a lengthy purification process. There are lots and lots of steps in it. At each step, we're actually going to lose a little bit of our product, transfer losses, and so on. So at each of the steps of these purification processes, we're going to lose a little bit of product. And last but not least, reaction did not go to completion. Organic reactions very rarely do actually go to completion. So the type of reaction this is, we've covered this before when we looked at the reactions at the beginning, and this is nucleophilic substitution. And we're going to cover that mechanism later on in the pack. Okay, so that finishes looking at that core practical 6. The preparation of bromobutane from butan-1-ol. Hopefully these videos, along with the PowerPoint, we should also be going through, have helped you complete the notes up to page 9, which was the work for this week. Remember, if you've got any questions or you're running into any problems, do email us or you can message us through Teams. But that's all for now, so take care, stay safe, bye-bye.